This video covers Module 1, Part 2, so please make sure you're completing the guided notes that go along with this section. And in this section, we're going to cover applications of linear equations. A hint is when you typically see the word applications, it means word problems. So we're going to go over first some key ways to translate from word problems to algebra, those steps, and then do a bunch of examples. So should be a good time. So when it first comes to translating from words into equations, we need to know where we get our equal sign and where that's going to go. And they aren't always going to use the word equals. They might use the word gives or yields or is the same as or is, was, or will be, right? So the sum of x and a number is, the sum of x and 4 is 5 would be a good example, right? The sum of x and 4 is 5, and that allows us to solve for x. Notice I said sum, not add. There are words for our main operations of addition, subtraction, and multiplication, and division as well. So for addition, the one word that might be a sticking point for some is the word sum. Sum is another word for addition, as well as the others in this list, and you can fill out the table in your guided notes. For subtraction, we're looking for the difference. They might also say less than or is decreased by. For multiplication, the sticking word tends to be product. When I multiply two numbers, I'm finding the product of those numbers. I could also say twice. That means I need to multiply by 2. I could say thrice, which is kind of a silly word, but that means multiplied by 3, or quadrupled, that's by 4. For division, the sticking word is going to be quotient. When we're dividing, we're finding a ratio. We'll be looking more at those in Module 6 as well, right? So these are our first steps. Our first steps are the building blocks of how to take the words and turn them into an equation. So when we're solving word problems, the first things I want you to do are read the problem carefully. And most people don't like to have to read in a math class. I'm so sorry, but you need to read the problem and think, what information is missing? What information do I have and what do I need to find? Then I recommend always assigning a variable to represent the unknown value. X and Y are great, but if you're working to figure out, the number of bananas, you might want to use a B. The number of cookies, you might want to use a C, something to keep your life easy. Again, I do avoid using S and T because S looks like a 5 and T looks like a plus sign. So I personally avoid those two variables as much as I can. Then sketch it out, right? If you need to make a table, if it's a perimeter problem or an area problem, draw a picture, anything to help you visualize. Write out your equations, solve those equations, and state your answer. Keep in mind, when we're making word problems, we want them to be representative of real-world problems. So the coffee didn't cost $150, right? The car was not going 600 miles per hour, right? We're trying to figure out and solve real world applications, so the numbers need to make sense. So check your answer to make sure it seems reasonable, and then always check your solution in your original equations just to catch any possible math errors. So let's take a look at some mini examples and then move on to some examples with a few more parts. So our first mini example, the difference between a number and 9. Well, we're going to translate that into an expression, an equation, or an inequality. In this case, I don't see a word that says is or equals, right? So for difference, that means subtraction. A number, I don't know what the number is. That's kind of a clue to assign a variable, and 9. So here would be the difference between a number and 9. We always take the first and the difference of the second, right? 3 less than a number is 14, right? So if I have a number and I take 3 less than that, so that might be subtracting by 3, that's my equal sign, 14. A number, that's x, is increased by the product of 6 and a number. So some number is increased by the product. So we're going to multiply 6 and a number. So I could write that as 6x or 6 times x. That's just an expression. It's not an equation because there's no equal sign. 5 times the sum of a number and 2 is less than 15. 5 times this whole thing, the sum of a number and 2, some number plus 2 is less than 15. So there we have an inequality. We're going to look at more at those in our next module. And then the quotient of 5 and a number is at most 10. So the quotient of 5 and a number, the number, what's listed first is always the numerator, is at most negative 10. What does that mean, is at most? Well, like I said, we're going to cover this more in the section on inequalities, but is at most means it could be less than or it could be equal to. It's at most, so that means it could be negative 10, but it also could be less than negative 10. So it's less than or equal to. So here we have some more single variable examples, and now it's asking us to solve them, to find the number. So the sum of a number and 6 is negative 3. Find the number. So if I have x plus 6 is negative 3, I can subtract 6 from both sides to see that, oh yeah, that number is negative 9. In example 2, I have the product, that's a clue that I'm multiplying. The product of a number and 4 is negative 28. So x times 4 is negative 28. And I want to rewrite this like 4x. We always want our constant before the variable. And now I know how to solve this. I divide both sides by 4, and I get x is negative 7. For our third example, the quotient, okay, so the quotient, that's a hint that I'm dividing, of twice a number and 6. Twice a number, that's my numerator. So I've got x times 2, and 6 is, that's my equal sign, 8 less than the number. So the same number, the number, and 8 less than that. In order to solve this, I'm first going to multiply both sides by 6 in order to get rid of the denominator. This would give me, and I'm sorry there's not a ton of room, 2x equals 6x minus 48. I combine like terms. I get negative 4x is negative 48, so x is going to be 12. These next two examples are consecutive integer examples. These are some of my personal favorites. So here I have two consecutive integers have a sum of 71. Find the integers. Well, let's take a look at what consecutive integers are. By consecutive, I mean they follow each other. So I could have 3 and 4, I could have 5 and 6, I could have 21 and 22, right? There are tons of consecutive integers. And I don't just want to look at the whole list to figure out which two add up to 71. What I notice about consecutive integers is they differ by 1. So if I have some integer x, the number after it is going to be x plus 1. So if I take the sum of two consecutive integers, I could have x plus 1 equals 71. This is an equation in one variable that I can solve. So I'm going to go ahead and combine my like terms. So I have 2x plus 1 equals 71. Subtract 1 from both sides. 2x is 70. Divide by 2, x is 35. So if x is 35, the two consecutive integers are 35 and 36. And we can check our work by adding those two together. In example 5, I have 3 consecutive odd integers have a sum of 39. Find the 3 integers. Well, what do I know about consecutive odd integers? I could have 3 and 5. I could have 7 and 9. I could have 21 and 23. Well, I notice that each of them differ by 2. So I'd have x and x plus 2. Now that's just two of them. What if I wanted to find the third? Well, I could look at 7, 11, and 25. See how this one differs from the first by 4. 21 and 25 have a difference of 4. 7 and 11 have a difference of 4. 3 and 7 have a difference of 4. So I'm going to put x plus 4. So the sum of those is 39. I now have my equation in a single variable. I'm going to put a plus there. So I combine like terms. I have 3x plus 6 is 39. 3x equals 33. X equals 11. So my integers would be 11, 13, and 15 that add up to 39. Let's start working on writing an expression for a real world situation. So now this is more applicable than just finding a number, kind of telling you straight out. So Sarah sold 10 more adult tickets than child tickets. We want to write an expression to represent adult tickets using the variable x for child tickets. So we have x for child tickets and maybe capital A for adult tickets. So Sarah sold 10 more adult tickets than child tickets. So how could I have the number of adult tickets equal to the number of child tickets? Well, she sold 10 more adult tickets. So in order to make these two amounts equal, right, here's if you kind of think of it as a bar graph, here's the number of adult tickets, here's the number of child tickets, and we know that she sold 10 more. So in order to make these two kind of equal, I would have to add 10. And for this problem, it just wanted us to set up the problem. In the second example, I have the length of a rectangle is 25 inches less than the width. And that's a little confusing because that honestly makes it one of these kind of rectangles, right? Here's my length and here's my width, right? So the wording's not super great on this one. But if I want to write an expression to express the length, if my length is 25 inches less than my width, in order to make them equal, I would have to subtract 25 from my length. So for example 1, Lauren, that's me, found that it takes 3/4 of an hour a day to drive the 15 minutes to work. I'm a slow driver. This is very close to true. What is the average rate of speed given that distance equals your rate of speed times time, right? So we're trying to find, we've been given a time, we've been given a distance, but we don't know our rate of speed. So let's set this up and then we can solve for our missing variable. So I know that it takes 15 miles. We don't know the rate of speed, but we know it takes 3/4 of an hour, right? So I can solve this two ways. I could multiply by 4/3, that's the reciprocal, or I could divide both sides by 3/4 of an hour, or 0.75. I'm going to multiply by 4/3. And I would get 60 over 3 equals R. So 20 miles per hour would be the rate that Lauren drove. The second example is a perimeter problem. You are going to see a lot of these over the course of this course, right? So the length of a rectangle is 1 centimeter more than twice the width. The perimeter of a rectangle is 110 centimeters. Find the length and width of the rectangle. So the equation for perimeter is 2 times width plus 2 times length, and I know my perimeter. I also know that the length of a rectangle is 1 centimeter more than twice the width. So I have, my length, and I have my width, and I double my width, right? So this would be 2 W's, but the length of this is still 1 centimeter more, right? So in order to make these both equal, I have the length equals 2w plus 1. Now I can start substituting in because this is 2 variables. Well, this one's 3, right? I need to start filling in with what I know. Well, I know 110 is my perimeter, and I have 2L plus 2W plus 2L. I also know exactly what my length is. My length is 2W plus 1. So I'm going to substitute in for L 2W plus 1 because they're equivalent. I could substitute them. I can change them out. So I'm going to have 110 is 2W plus 2 times 2W plus 1. Then I can go ahead and distribute that 2, combine like terms, and solve for W and get that W is 18. So my width is 18. How much is the length? Well, the length is 2W plus 1. So my length is 2 times 18 plus 1, and that gives us 37. My length is 37. In example 3, during the 2009 regular season, Justin Verlander of the Detroit Tigers and Tim Lincecum of the San Francisco Giants were the top major league pitchers in strikeouts. I guess that's very good. So the two pitchers had a total together of 530 strikeouts. Verlander had 8 more strikeouts than Lincecum. So how many strikeouts did each pitcher have? So the first thing I know is that Verlander and Lincecum together had a sum of 530. I also know that Verlander had 8 more strikeouts than Lincecum. So Verlander would be equal to Lincecum if we give Lincecum, I don't know if I'm pronouncing that right, an additional 8. Now I have 2 equations and 2 variables, but I can substitute. I know what V is. I can substitute in for V, L plus 8. So I could rewrite this as L plus 8 plus L equals 530. So I have 2L plus 8 is 530. 2L is 522. So if I divide both sides by 2, L is 261. So Lincecum had 261 outs. But I also need to know how many Verlander had. So I can substitute this back in to find out that Verlander had 269. Perfect. For our next example, we have to also keep in mind that coins, while we can count them, they also have a value. So if I have 3 quarters, that's 75 cents, right? So I have a number of quarters, but then that number of quarters also has a value. So in example 4, for a bill totaling $5.65, a cashier receives 25 coins consisting of nickels and quarters. So I'm going to use N and Q, and the number of where N and Q are the number of coins. The number is different than the value. N and Q is 25. Those coins' value is $5.65. Well, how do I figure out the value? Well, I would take the number of coins I have times their worth to get their total value. So I'm going to have 0.05, so is a nickel's worth 5 cents, plus 0.25 times Q, because a nickel's worth 25 cents. Sorry, a quarter is worth 25 cents. Now I have 2 equations and 2 variables. I need to figure out how to substitute in for one of them, and I'm going to substitute in for N. I can rewrite this first equation as N equals 25 minus Q. I could also have solved this problem for Q, but I decided to solve it for N instead. I can now substitute this in to my second equation. So I'm going to have 0.05 times 25 minus Q plus 0.25Q equals $5.65. 0.05 times 25 is 1.25 minus 0.05Q plus 0.25Q is 565. I have 0.20Q is, once I subtract $1.25 from both sides, $4.40. I divide both sides by 0.20, and I get that Q is 22. So I have 22 quarters. Well, how many nickels do I have? I can substitute that back in. N is 25 minus 22, so I had 3 nickels and 22 quarters. This next example tends to be people's least favorite. It's always like, how long did it take 2 trains to cross each other's path if they leave the station? But they're really less complicated than they sound. So if 2 trains leave stations 280 miles apart at the same time and travel towards each other, one train travels at 105 miles per hour, while the other train travels at 95 miles per hour. How long will it take for the 2 trains to meet? Keeping in mind that distance is rate times time. So everyone starts by doing something kind of complicated. I'm like, okay, here I have train 1, and here I have train 2, and they're going different speeds, and how long will it take for them to meet? Well, by the time they meet, they've gone all 280 miles. So 280 is our distance. And the rate it's going to take each train to go those distance would be the same amount of time, right? How long is it going to take for them to meet? That's just one time. What's different is the rates. So I look at how long it would take the train going 105 miles per hour in the same amount of time as the train going 95 miles per hour. And I know I used t, which is a terrible variable to use. So I'd have 280 is 200 t, because together that's how fast they'd be going. I divide both sides by 200, and I get that our time is 1.4 hours. So they would meet up, they will have both crossed the total 280 feet, and it does miles, and it doesn't matter that one went further than the other. It would still take them both 140 hours to cross that distance together. So that's how long it would take them to meet. Another type of problem we're going to see is these interest problems. So a thing for us to know is that interest equals principal times rate times time. And I believe we saw this in mathematical models. So if I have $250 to invest, what we invest, that's our principal. I want to invest that in an account that has 2% annual interest. That's my rate, but I need to write it as a decimal. And I want to know how much it will earn after 15 years, where our time is always in years. So my interest is going to be our $250 times my rate of 0.02 times 15 years. That's how I'm going to calculate my interest. So I have 250 times 0.02 times 15. That's going to give me 75. So the interest that I would earn in 15 years on $250 is $75. So that's pretty good amount. The last 2 examples involve a table method for word problems. That's just a way to keep your information organized. And both of those have some kind of pre-questions to get us to start thinking about these issues. So I like to talk about Arnold Palmer. I don't know if you know what an Arnold Palmer is, but it's half tea and half lemonade. So my question for you is, if I have 10 cups of Arnold Palmer, how much lemonade do I have? Well, I already told you it's half, right? So what's half of 10? That's 5. I could take 0.5 times 10 and get 5 cups. I'd have 5 cups of lemonade. So if I have a mixture of 2 things together, and I know what percent is of part of that mixture, in this case lemonade, I would multiply by 0.5 or 1/2 in order to figure out that full amount of lemonade I have. So let's say I have an unknown amount of cups of Arnold Palmer. How much lemonade am I going to have? Well, since it's half lemonade, I'm going to have 0.5 times x. And you might be, okay, why is she talking about lemonade? Other than the fact that it's very hot on the day I'm recording this. is we're going to see this in examples in chemistry, and I know a lot of you end up taking chemistry courses. So for example, a chemist must mix 8 liters of a 40% acid solution. So that's a solution that's 40% acid and typically 60% water, right? But it's 40% acid. And they're going to want to mix that with some 70% solution to get a 50% solution. And I need to know how much of the solution should be used. So this is when we're going to want to make a table. I always do this for these type of problems, right? So I know that I need to mix 8 liters of, this is of my solution, so liters of solution. That is 40%, so I'm going to write that as 0.50, that's my percent acid. I'm going to mix that with some unknown amount of a 70%, and I should get a 50% solution. Well, if I take 8 liters and add in X unknown liters, right, of a solution, I'm going to have 8 plus X liters total. And then I take my liters of solution times my percent acid to get the liters of pure acid. Just like we did for the cups of pure lemonade in an Arnold Palmer, we multiply the amount we have times the percentage. So I'm going to take 8 times 0.4 and X times 0.7, so 0.7X. And my total amount and my desired concentration, that's 0.50 times 8 plus X. Now, the amount of pure acid in each of my individual solutions, the 40% and the 70, is going to be the same as the amount of acid when I mix them together. These are going to be equal. So I have, this is 3.2, by the way. So I have 3.2 plus 0.7x equals 0.5 times 4 plus x. And I can distribute. I've got 3.2 plus 0.7x is why did I write 4? I was doing the math in my head. Sorry, guys. 0.5 times 8, that's 4. Half of 8 plus 0.5x. And now I combine like terms. I subtract 4 from both sides. I minus 0.7x from both sides. And I get negative 0.8 is negative 0.2x. That's going to give me x is a positive 4. So I need to mix 4 liters of 0.70 acid to 8 liters of 40% to get, I guess I would get 12 liters of 0.50 acid. We can also use this table method to keep track of our pieces when we're solving interest problems. We've already done one interest problem. Let's do one a little more complicated. So building up to that, if I have $100 that I have to invest in an account that earns 0.01 or 1% annual interest, how much interest will I earn after 1 year? And we know interest is principal times rate times time. So my time is 1 year. It kind of just goes away because any number times 1 is just itself. Well, I have my interest would be 0.01 times 100. So $1. In 1 year, I would earn $1. But what if I invest an unknown amount of money at that same rate? Well, in this case, my interest would be 0.01 times that unknown amount would give me the interest I need to find. So, last example of this video, I promise. I have Thomas, and Thomas has $40,000 to invest, and he wants to put part of the money into an account paying 4% and the remainder into an amount paying stocks. And what he wants to earn from these investments should be $2,040, okay? So, that's my table drawing sound. So, we have, in the end, he's going to have $40,000 that he invested, and he's going to earn $2,040 of interest. So this is our interest, And this is the amount invested. Well, the amount invested times your rate is going to give you that interest. We're looking at two different accounts together, so we really don't need this section right here. My two rates are 0.04 and 0.06. Let's let 0.04, that's that first account. So let's say I invest X in that account. It's very tempting to want to put a Y right here. I'm actually not going to do that because what I want us to think about is if I invest X dollars, how much do I have left, right? If I invested $10,000, I would have 40,000 minus 10,000 left. If I invest 5,000, I'd have 40,000 minus 5,000. So if I invest X, I'd have 40,000 minus X. And this whole row is going to add up to 40,000, just like our interest on both accounts is going to add up to what our desired income is on those investments. And I multiply our principal that we've invested times our rate, 0.04x, 0.06 times 40,000 minus x. These, much like in our last example, are going to be equal. So I have 0.04x plus 0.06 times 40,000 minus x is 2,040. So I have 0.04x plus, it's going to end up being 2,400 minus 0.06x is 2,040. And I combine like terms, I get negative 0.02x. I move the 240 to the other side, and I get negative 360. I divide both sides by negative 0.02, and I get a positive $18,000, right? And our amount should always be positive. You can't invest negative money. So we invest $18,000 at 4%. Well, then how much is at 6%? Well, it's going to be that 40,000 minus our X, which in this case was 18,000. And I would have 22,000 left to invest at 6%.